Today's topic is Raman Effect. When a beam of light is passed through a transparent substance, a small amount of radiation energy is scattered. If monochromatic radiation or radiation of a very narrow frequency band is used, the scattered energy will consist almost entirely of radiation of the incident frequency. It is known as Rayleigh scattering. But in addition, certain discrete frequencies above and below that of the incident beam frequency will be scattered, which is referred to as Raman scattering. So, when a beam of light is passed through a transparent substance, in the scattered light we have three types of radiation. One of incident frequency and other two are larger than incident frequency and lower than incident frequency. If in scattered radiation we get radiation of incident frequency, then this is known as Rayleigh scattering. And if we have radiation which have frequency greater than or lower than the incident beam frequency, this is known as Raman scattering. Quantum theory of Raman effect. The occurrence of Raman scattering may be most easily understood in terms of quantum theory of radiation. This treats radiation of frequency nu as consisting of a stream of particles called photons having energy h nu. So photons are treated as particles, and if they have frequency nu, their energy is h nu, where h is Planck's constant. Photons can be imagined to undergo collisions with molecules, and if collision is perfectly elastic, they will be deflected unchanged and scattered energy will consist radiation of the incident frequency. This is Rayleigh's scattering. So, if we see that beam of light is passed through a transparent substance, beam of light is made up of photons. Photons of frequency nu have energy h nu. If these photons collide with molecules, and if this scattering is elastic scattering, there will be no change in energy. And if energy is not changed, then frequency is also not changed. So we have scattered energy will consist radiation of the incident frequency, which is Rayleigh scattering. However, it may happen that energy is exchanged between photon and molecule during the collision. Such collision are called inelastic collision. The molecule can gain or lose amount of energy only in accordance with the quantum laws. That is, its energy change delta E must be the difference in energy between two of its allowed states. That is, change in energy delta E must represent a change in the vibrational and or rotational energy of the molecule. If the molecule gains energy delta E, the photon will be scattered with a energy h nu minus delta E. Photon collides with molecule, and if molecule gain energy from photon, then photon energy will be h nu minus delta E. Delta E is the energy gained by the molecule from the photon. So initially photon energy is h nu, and if it give delta E energy to the molecule, then energy of scattered photon will be h nu minus delta E, and the equivalent radiation will have a frequency nu minus delta E upon h. This is the energy of scattered photon when it give a delta E energy to molecule. Energy is h nu minus delta E. If we want to find the frequency, we have to divide it by h. So if we divide by h, then it gives the frequency, and it will be nu minus delta E upon h. Conversely, if the molecule loses energy delta E, the scattered frequency will be nu plus delta E upon h. If molecule lose energy, then energy of photon is increased and frequency of photon is also increased. So in scattered radiation, we can have the radiations of frequency lower than incident frequency, that is nu minus delta E upon h, and greater than incident frequency, that is nu plus delta E upon h, and it depends on whether the photon gives some energy to molecule or photon gains some energy from the molecule. Radiation scattered with a frequency lower than that of the incident beam is referred to as Stokes radiation, while that at higher frequency is called anti-Stokes radiation. Since the former is accompanied by an increase in molecular energy, which can always occur subject to certain selection rules, while the latter involve a decrease in molecular energy, which can only occur if the molecule is originally in an excited vibrational or rotational state. Stokes radiation is generally more intense than anti-Stokes radiation. Most of the molecules remains in ground state, and only few of them remains in excited state of higher energies. If molecule, so it is the probability of molecules to gain energy from photon is larger, because most of the molecules are in lower energy state, ground state. And for a molecule to lose energy, its probability is lower, because molecule can lose energy only if it is in excited state, and molecules in excited states are in a small number in comparison to the molecules in ground state. So the probability of Stokes radiation is larger, in which we find scattered radiation of a smaller frequency. Classical theory of Raman effect, molecular polarizability. When a molecule is put into a static electric field, it suffers some distortion. The positively charged nuclei being attracted towards the negative pole of the field, the electrons to the positive pole. This separation of charge centers cause an induced electric dipole moment to be set up in the molecule, and the molecule is said to be polarized. So if a molecule is placed in an electric field, their positive and negative charge centers are displaced, and it becomes a dipole having induced dipole moment. Induced dipole moment mu depends both on the magnitude of applied field E and on the ease with which the molecule can be distorted. We may write mu equal to alpha E. Mu is induced dipole moment and it is proportional to applied electric field. The larger is the electric field, the separation of positive and negative charge will be larger and induced dipole moment will be larger. So mu is proportional to E and mu is equal to alpha E. Alpha is constant and it is known as polarizability of the molecule. Considering diatomic molecule H2 placed in an electric field, we find that the electrons forming the bond are more easily displaced by the field along the bond axis. Figure B. This is the figure B. Hydrogen molecule is shown, and in this the field is applied along the axis, along the bond acting between these two hydrogen atoms. We find that the electrons forming the bond are more easily displaced by the field along the bond axis than that across the band, across the bond. It is not band. This is the case shown in figure A when field is applied perpendicular to this bond. So when field is applied along the bond as shown in this figure B, then electrons are easily displaced by the field in comparison to this case when field is applied perpendicular to the bond. So dipole moment or this constant alpha, which is known as polarizability, depend on along which direction the field is applied. The polarizability The polarizability is thus said to be anisotropic. It depends on the direction of the applied field. The polarizability of a molecule in various directions is conventionally represented by drawing a polarizability ellipsoid. For hydrogen, its general shape is like that of a squashed sphere, like a tangerine. This is shown in this figure. In general, a polarizability ellipsoid is defined as a three-dimensional surface whose distance from the electrical center of the molecule is proportional to 1 upon under root alpha I, where alpha I is the polarizability along the line joining a point I on the ellipsoid with the electrical center. Thus, where the polarizability is greatest, the axis of the ellipsoid is least, and vice versa. In this case, if we have a spherical surface, ellipsoid is spherical. Here the polarizability is same at all points on the surface of the sphere because the distance from center is same. Here, if the polarizability ellipsoid is of this shape, then we have two axes. One is larger, major axis, and other is smaller, that is minor axis. So if a molecule, if we consider a point on minor axis, small axis, here the distance is small, distance from center to the surface point is small. It means that this distance, as it is proportional to 1 upon root alpha I, this distance is small, then alpha I is larger. So in this direction, polarizability is larger, where this distance is small. And if we see the direction along the major axis, here the distance is largest. So here in this direction, polarizability is smallest. So distance of a point on the surface of ellipsoid from its center gives the polarizability. Where this distance is small, polarizability is large. All diatomic molecules have ellipsoids of the same general tangerine shape as hydrogen, as do linear polyatomic molecules such as CO2, C2H2. They differ only in the relative sizes of their major and minor axes. When a sample of such molecules is subjected to a beam of radiation of frequency nu, the electric field experienced by each molecule is E equal to E0 sine 2 pi nu t. E equal to E0 sine omega t, and omega angular frequency is 2 pi nu. nu is the frequency. So we write electric field as E equal to E0 sine omega t, and we write omega as 2 pi nu. If electric field is of this type, then induced dipole moment mu is equal to alpha E. So it is equal to alpha E0 sine 2 pi nu t. Such an oscillating dipole emits radiation of its own oscillation frequency. Oscillation frequency here is nu. So such an oscillating dipole emits radiation of its own oscillation frequency. This gives the explanation of Rayleigh scattering. In scattered radiation, we have radiation of original frequency nu. If in addition the molecule undergoes some internal motion such as vibration or rotation which changes the polarizability periodically, then the oscillating dipole will have superimposed upon its vibrational or rotational oscillation. Consider, for example, a vibration of frequency nu VIB. VIB is for vibrational, and if we consider vibrational motion and frequency of vibrational motion is nu vibrational, then it changes the polarizability as alpha equal to alpha 0 plus beta sine 2 pi nu vibrational into t. Here we have, initially we assume alpha as constant, then we find the frequency nu, frequency of oscillating dipole, and now if we consider the vibrational motion of molecule, then this alpha is now changed, and we assume alpha equal to alpha 0 plus this term is beta sine 2 pi nu vibrational into t, sine omega t, and here for omega we write 2 pi nu VIB. Here alpha 0 is the equilibrium polarizability and beta represents the rate of change of polarizability with the vibration. Now we have induced dipole moment mu equal to alpha E. Put the value of alpha, which is alpha 0 plus beta sine 2 pi nu vibrational t, and into E0 sine 2 pi nu t. On expanding and using trigonometric relation, sin A sin B equal to half cos A minus B minus cos A plus B. If we solve this expression for mu, we have two terms. First term is alpha 0 into E0 sine 2 pi nu t, which is written here, alpha 0 E0 sine 2 pi nu t, and other term is this beta 2 pi nu VIB t E0 sine 2 pi nu t. Here we have two sine terms, sine 2 pi nu VIB t into sine 2 pi nu t. So we use the formula sin A sin B. Sin A sin B is half cos A minus B minus cos A plus B. So we have half. This is the first term of using cos A minus B. Beta E0 are written before this term, and we have cos A minus B, then we have cos 2 pi nu minus nu vibrational t. Then other term is minus cos A plus B, then we have minus cos, and these are the term A plus B, 2 pi nu plus nu vibrational into t. So we have three terms. In first term we have frequency equal to nu, that of frequency of incident radiation. And in other two terms we have frequencies nu minus nu vibrational and nu plus nu vibrational. And thus the oscillating dipole has frequency components nu plus minus nu vibrational as well as the exciting frequency nu. It should be noted that if the vibration does not alter the polarizability of the molecule, then beta is 0 and the dipole oscillates only at the frequency of the incident radiation. The same is true for a rotation. Thus we have the general rule: in order to be Raman active, a molecular rotation or vibration must cause some change in a component of molecular polarizability. A change in polarizability is of course reflected by a change in either the magnitude of or the direction of the polarizability ellipsoid. So in scattered radiation now we have three types of frequency nu and frequency nu plus nu vibrational and nu minus nu vibrational. If we have frequency nu minus nu vibrational, frequency of scattered photon is reduced. These gives Stokes lines. And if we have frequency nu plus nu vibrational, frequency of scattered photon is increased and this gives anti-Stokes lines. So this is the classical explanation of Raman effect.